Hi. In the last video, we considered the auto-dissociation of acids. The acid HA reacting with water dissociates to A minus. The water picks up a proton to H3O plus. The equilibrium, the N line, will be the concentration of the acid, will be the initial concentration Ma minus, the amount dissociated. X is the amount dissociated. The amount of H3O plus is also X. And we know from the law of equilibrium constants that the reactant concentration, the product concentrations divided by the reactant concentrations, which in this case is Ma minus X, that this is the equilibrium constant, the acid equilibrium constant. And in the last video, we considered the case of Ka much larger than Ma, and we found out that in this case, the expression simplifies a great deal. If Ka is much larger than Ma, it turns out that to the sig figs that we know the actual values, the value of X is equal to Ma itself. And in this video, we're going to consider the flipped case. We're going to consider the case where Ma is much larger than Ka. So if Ma is much larger than Ka, that means that this number here is small. And if this number is small, that means the amount of product is small. So very little has reacted. X is small. And that means that if it's very small, that Ma is big compared to it, and because Ma is the big number, Ma is going to be larger, much larger than X. So in the case where Ma is much bigger than Ka, we have very little reaction, very little product, and therefore X is very small, much smaller than Ma. And let's write that out then. We have X squared divided by Ma minus X equals Ka. And let's do some example. We'll choose Ka to be 2.6 times 10 to the minus 9, a very small value. We'll choose Ma to be a relatively big value, 2.8 times 10 to the 0. The order of magnitude of Ka, since it's 2.6 times 10 to the minus 9, is minus 8.5. The order of magnitude of Ma is 2.8 is equal to 1/2, and we're going to assume that X is very small compared to Ma, therefore the order of magnitude of Ma minus X is unchanged. The X has not changed it. Its order of magnitude will also be 1/2. X didn't change it. So we have here the situation that we have a order of magnitude of the denominator 1/2, and the order of magnitude of Ka is minus 8.5. And the question then is, what must the order of magnitude of X be? So please pause the video and see if you can figure out what the order of magnitude of X is in this scenario. So if you got that the answer was negative 4.5, negative 4, you got the right answer. And why is that? Because remember that we combine these two numbers. So 1/2 minus 8.5 is negative 8, and that is the order of magnitude of X squared. So if the order of magnitude of X squared is minus 8, the order of magnitude of the square is always double, the order of magnitude of x is equal to minus 4. And that confirms our suspicion. The order of magnitude of x is minus 4. The order of magnitude of MA, on the other hand, was 1/2. A number that's of order of magnitude 1/2, when you subtract a number of 100,000 times, 50,000 times smaller than it, it just doesn't change to 2 sig figs. Just a tiny amount of MA went away. So indeed, the order of magnitude of MA minus X is also 1/2, which was the assumption that we made. And so in the scenario where MA is much, much bigger than KA, the equation x squared divided by MA minus X simplifies to this form. We can ignore the x in the denominator, and we can find the value of x from the equation x squared divided by MA equals KA. The equation x equals MA is when KA is much, much larger than MA. The equation x squared divided by MA equals KA is true when MA is much, much larger than KA. And those are the two asymptotes, the two extreme regions.